All right, we're moving into the heart of our study of atoms right now. So far from chapter 6, basically we talked about light, and I said a number of times that we would use light as a tool to learn things about atoms. Now is the time to start looking at how we can do that and what exactly we have learned from atoms, learned about atoms by checking out their interactions with light. Okay, what we're going to talk about in this video is the idea of atomic spectra, atomic emission spectra primarily. Okay, what happens here is an atom, when it says excited atoms, that means an atom that for some reason or other has some excess energy in it. Okay, there has to be some sort of energy source that pumps that energy into the atom. The atoms will then emit light. You're familiar with this in the form of neon signs, among other things, right? Neon sign like, I don't know, a beer sign in a bar or something like that is the different colors of light that come in there are made by filling the tubes of the sign with different kinds of gas. So emission from different elements is in different colors. So you see different colors of light emitted based on what element is actually present in the sample that's emitting the light. Any particular element then is only emitting certain wavelengths. Remember, the wavelength correlates with what color the light is. So when I say if I fill up the tube with a particular gas, it will look a given color. That means it's emitting light at those wavelengths that we see as that color, but not at other wavelengths. Otherwise, we would see it as white. Okay. This is referred to as being a line spectrum, or the spectra consists of what are sometimes referred to as spectral lines. The idea of lines there is somewhat related to one of the ways to look at these spectra or how they were historically measured. So let's go ahead and take a look at how we would observe one of these spectra. So this is a diagram from the textbook, and it shows, in this case, what would be a continuous spectrum, okay? So this is not what we see when we look at these excited atoms, but when it says continuous, what that means is this says I take white light, maybe I just take sunlight or light from a good light bulb. I take that light, in this case, I pass it through a couple of slits. That's mainly just to make it be a beam rather than just a wide spot. So now I have a narrow bit of light that comes into the prism. The prism will separate the light into its wavelengths, and you'll see on the screen downstream on this end that we can see all of the colors of the rainbow, as it were, in the spectrum. Okay, that means all wavelengths are present. That's why when we look at that with your eye before it goes through the prism, you see it as white light. White light is the combination of all of the different colors. Okay, so that's a continuous spectrum. And what the word continuous refers to is the fact that all the wavelengths are in there, right? There are no wavelengths that are absent. It's not like the light is all one particular color after it comes through the prism. Next up, we're going to look at what happens if we really want to take an atomic spectrum where we see this line spectrum idea, okay? So now my source, instead of being just a white light from the sun, I've got a tube down here, what says gas discharge tube. What the discharge means is it means on the ends of that tube, on the top and bottom here, coming in where those white lines come in from the side, picture those as being wires that go to a power supply. And that power supply is going to put a fairly large voltage across the ends of that tube. Something on the order of a few thousand volts typically is what we would want to have there, okay? My tube, in this case, it says is filled with hydrogen, okay? If the tube is filled with hydrogen gas, the hydrogen gas in the tube, when it's just hanging out, is going to be H2, just like we always think of hydrogen as being H2. But when I turn on the power supply and I put this 5,000 volt potential across the two ends of the tube, what's going to happen is, first of all, that's enough energy to take the H2 molecules and just to tear them in half. So I'm going to get actual H atoms in there just because there's so much energy present. It's enough to break the forces, break the bonds that hold the H's together and separate them into atoms. As it does that, some of those atoms are also going to be carrying away excess energy, and that's going to be emitted. That's the light that's coming out of the tube. So the tube will glow when this is going on. If we were having in-person live class, I would have a set of these tubes and a little contraption to stick them in, and we'd be able to watch them light up different colors. I've got some pictures for us here. It won't be quite the same. But then I have the light coming out of my tube. I'm again going to pass it through the slits, right? So here I've got my two slits, which are just making my light into a collimated beam of light. Send that into the prism and now look downstream on the slide again. And when I look down here, what I see is very different from the continuous spectrum, right? So now within the part of the spectrum that the human eye can see, it turns out there are exactly 4 wavelengths of light that are present, okay? And they're reflected there or represented there by the 2 blue lines. There's a green one and there's a red one because that's the colors they would appear. Okay, all of the other wavelengths are missing. So this is not a continuous spectrum. This is sometimes called the discrete spectrum. It's called a line spectrum mainly because if we take the spectrum in this way, what we see on the screen down here are this series of lines where each line corresponds to a different wavelength. Okay, so that's very different from what we see just with white light going in there. All right. The claim is that if we change what gas is in the tube, change it from hydrogen to helium, for example, or to something else, we would see different wavelengths down there, okay? All the places where my screen is black, those are wavelengths that are not being emitted by the gas in my tube. Okay, so something unusual is happening here that allows the gas to emit just a few different wavelengths of light. Remember, the wavelength in our photon picture corresponds to energy. So this says the energy that's being emitted by that atom can only come out in certain increments, in certain allotments, sort of. This is, oh, I just picked helium at random and that was what was next. I didn't actually realize that. This is a spectrum, the picture's not the greatest, but this is a picture that I actually took a pretty long time ago with an older camera, so the resolution isn't great. But this is emission from a tube of helium, again with that that large potential, 5,000 volts or so across the ends of the tube to excite the atoms. The picture was taken looking through a sheet of clear plastic that is actually a diffraction grating. What that means is it's got a lot of very closely spaced lines printed on it. You can see through it. It doesn't show up the lines because they're really thin, and the separation between those lines is going to be on the order of the wavelength of visible light, okay? And that's what separates the light out into colors. It's doing the job of the prism in the previous slide. And again, although the resolution isn't great, you can see there are some colors of light that are present. So the glow in the middle, this part in here, this is just what you would see if you just looked head on into this and you weren't really looking through the diffraction grating, right? But over here on this part, you can see where there are a few lines that are there. There's kind of a yellow one, maybe there's a blue one. The yellow one may be an artifact. There's a blue one, a green one. There's something kind of orangey out there. Those are the lines that are coming out from the light being emitted by the helium. And again, if we were in live class in the auditorium, I'd have a few of these and I'd be lighting them up and we'd be seeing the different colors go on through there. What I did instead is I just grabbed this picture. This is the light being emitted by a variety of different elements, okay? The one here, this is hydrogen, one of the ones I showed you. On the top, we've got what the continuous spectrum looks like, right? So this is all the wavelengths present. Sodium, hydrogen, calcium, mercury, those are chosen pretty much at random. They're just the elements that happen to be in this picture when I found it. If I look on the bottom, I've got wavelengths. These are in angstroms. So this is from 400 nanometers over here to 700 nanometers out here in the red part, okay? This slide just happens to be in angstroms, where there are 10 angstroms in a nanometer. And so it's just a different distance unit that used to be used pretty often in chemistry. It's used a little bit less often nowadays. And if we see this, we can see that there are different colors present for each element. There are different numbers of different lines present for each element, right? Hydrogen has the fewest of the ones that are on here. It looks like calcium has the most, at least here in the visible part of the spectrum, right? One reason why hydrogen has the fewest is that any given hydrogen atom only has one electron in it, right? Whereas these other atoms have lots of electrons in them, and that means there's more possibilities for how to move those electrons around among what we'll come to call energy levels very soon, okay? But this gives us an idea of just the fact that something peculiar is happening, all right? This is an experiment that first became doable around the beginning of the 20th century when people got adequate technology to be able to measure these things, and it's part of the whole generation of the ideas that we now refer to as quantum mechanics that we're going to be taking up over the next few classes, okay? So the idea that there are these only certain energies that show up, leads people to propose the notion that electrons in atoms are restricted to certain energy levels, okay? Effectively what's happening, and I'll show a diagram that shows this better in a moment, is that in that light being emitted, we see a few different colors. That means we see a few different photon energies coming out from the atoms, okay? So the atom can lose only certain amounts of energy. It can't lose an arbitrarily small or arbitrarily big amount of energy. It can only lose a few. That suggests that it has to hop between a set of energy levels. And so we'll draw diagrams starting, well, I guess now, that say we have energy going up as we go up the slide. There'll be an energy level at the bottom, and then there might be any number of energy levels above here, okay? And we'll say that the atom, the electron in the atom has to be at one of the energies that corresponds to one of those energy levels. We say this means the energy is quantized. Quantized means restricted to only certain allowed values, okay? This is a very strange idea. Macroscopic objects never appear to behave this way to us. There are reasons for that, but for things on the scale of atoms and molecules, this idea of quantized energy becomes very important to understanding them, okay? So how does that energy level diagram actually help us understand the fact that we see only those few wavelengths in the spectrum? I've got a diagram here, and this is the simplest possible atom. This atom has only two possible energy levels, okay? There are no atoms that actually are like that. Let me first do some better labeling on here. Let me again put an energy and an arrow going up to show that as we go up in the diagram, we're going to higher energies, okay? And what we have here for the emission part, this is a little bit like a before and after shot, okay? So over here, I'll label them to say that. On the left in my before part, I have the excited atom. So I have the gas in the tube, it's in the power supply. I flip the switch to turn the power supply on. When I do that, it pumps energy in. That energy takes some of the atoms where the blue dot here represents what energy state is the atom actually at. If it's the electron in the atom, where is it? What energy level it's in? So this says I start off up there in this excited state. So the power supply is what's gotten the atom up there, right? If I turn the power supply off, the atom's definitely not going to stay there because it's going to get to the lowest possible energy. But if my atom is in that excited state, it has a possibility that it could get rid of that energy, right? It wants to get rid of the energy. It does not want to be at a higher energy than it might otherwise be. If I were to hold my pencil up here and let go of it, it would fall down and land on my table because it would be going from a higher potential energy to a lower potential energy, right? That's just what my electron's going to do. If my electron wants to go from being in this high energy level back down to the bottom one, it has to do something with the energy, right? Energy has to be conserved. So the energy that the electron is going to get rid of, or the atom's going to get rid of, has to go someplace. In this case, it can be ejected or emitted as light. That means the energy is h nu. What does that say? That says that my atom or my electron is going from here down to there, right? So the energy, the distance in my picture, remember the vertical direction is energy. So the length of this arrow is an energy, and it has to be equal to h times nu. So what that tells me is that for every one of those lines that I see in my spectrum, in my atom, there's a pair of energy levels that are separated by an energy that matches the energy that goes with that wavelength, or the energy of that photon, right? So if I have an energy level here, if I had another energy level that was in the middle of these, then I'd have a possibility to go from here down to there. But if there's not an energy level there, then I can't do that, okay? And so if I only have the energy levels I started off with, then that hop is not allowed. I can only go from one energy level to another. It's a bit like being on a ladder where you have to be on one rung or the next, right? You can't be just hanging out between steps. You have to always be on one of them. That's exactly what applies here to our energy levels. This is emission because the light is coming out from the atom. We say the atom emits the photon, right? Light is being emitted. That's why it's called an emission spectrum. If I wanted to, I could do the experiment, at least in principle, in the other direction. I could start with my atom, and again, let me put the energy label on here, which I really should have put in when I made the slides. If I start off with my atom just hanging out where it belongs, down here in the bottom state, that bottom state is often referred to as the ground state because it's the lowest, okay? If I do this and I shine light on my atom, instead of turning on the power supply, that light is also a way that the atom could gain energy. If the atom absorbs the photon, so the photon approaches the atom takes in the photon, so the photon is destroyed, but its energy has to go someplace, right? So if this is h nu is an amount of energy, that energy has to correspond again to this amount of energy here, right? Going up, the vertical distance is energy. So the length of that arrow corresponds to energy. And this energy is again equal to h nu. Okay, in this case, the delta E here, that's the change in energy for my atom. In this case, the energy is gaining the energy from the photon, right? I skipped over the delta E part, but in my previous slide, I had the delta E was equal to the energy, but in this case, the atom is giving back out that energy, right? So the energy of the atom is going down in this picture, it's going up in this picture here, right? Either way, if it's the same atom with the same energy levels, the spacing between them is the same, and so the wavelength or the color of that light that I see is going to be the same, right? So the colors of light that we saw in that picture of the different spectra, those tell us something about what is the spacing between the energy levels in those different atoms. Okay, those also are one of the first bits of evidence that says that atoms really do find themselves restricted to only certain allowed energies. It can't just have any energy that it wants. Okay, again, that's a very non-intuitive kind of thing to say, because if you think about throwing a ball, you can throw it, it's going at one speed, and if you throw it just a teensy bit faster, it'll go by some infinitesimal amount higher energy, and so on, right? Electrons and atoms don't work that way. They can only have these limited number of allowed energies. It's weird. This is again, what would happen if I did this as absorption or emission, okay? And the reason why the pictures I showed you in the demonstration I would have been doing if we were in a normal classroom is emission, is frankly because it's a lot easier to see the different colors there, right? If I take the continuous spectrum, the emission spectrum says almost the entire continuous spectrum is missing. That means basically it's a dark background, and you just see the few colors that are there, okay? If instead I did that in absorption, that means almost all the colors are present, right? So if you look at that, it still looks a really lot like white light. It's just harder to see that there are a few wavelengths that are missing. So if I look down here, we see, for example, where here I see the red line there, down here there's a missing wavelength. It's much easier to see that, especially for the human eye, looking against the dark background, okay? Either one of these techniques or ways of looking at the spectrum can be used to identify something, and people do that a lot. Generally speaking, there's likely to be more lines visible in the emission spectrum than in the absorption spectrum, even though that's not true in this little diagram here, okay? There are reasons for that. I don't really feel the need to go into them right now, but essentially they're because in the absorption spectrum, normally all the atoms start off in their lowest state, so the only changes you can see are ones that start from there. If I was in the emission spectrum, might have other possibilities as well. So if you're wondering what this is good for, there's a couple of things. For our purposes, this is good for just getting us started on the track to thinking about atoms as having energy levels, okay? Some of you will have met up with that idea before in high school, for example, but we're probably gonna go a bit deeper into how we know that and what we can do with it than you might have before, okay? It turns out both atoms and molecules have spectra like this, where they absorb or emit certain wavelengths of light. These spectra are used all the time to identify samples, whether it's to figure out what elements are present in a sample or to figure out what molecules are present in a sample. This is done in lots of different fields. They do this, people do this in forensics labs if you just, somebody brings in a sample and they want to know if it's whatever somebody's being accused of having that is illegal, they have to test it and prove it's that stuff, right? One of the ways to do that is to look at what wavelengths of light it will absorb or emit. People also do this in astronomy and astrophysics. A lot of modern astronomy actually consists of looking at things and looking at the light being emitted in specific wavelength regions from different planets, stars, what have you. That's the source of just about all the information we have about what is the elemental composition of different parts of the universe, right? And it's very rich source of information. When people began to be able to do that, it tremendously expanded what we know about the universe. There's, gosh, just in the news as I'm recording this, there's a story in the last couple of days of detection of phosphine, which is taken as a possible sign of life in the atmosphere of Venus. And that also is a spectroscopic observation where people have seen absorption of wavelengths in the atmosphere of Venus that are known to correspond to this molecule called phosphine. Okay, phosphine is sort of like ammonia is NH3, phosphine is pH3, and so it's a somewhat analogous sort of molecule, but that is something also that's recently been detected by using these spectra.